All right, so my plan is to discuss briefly about the decomposition of amino acids in water, especially for the ocean world of Enceladus and Europa. And the whole idea is, we heard from the previous talk, we have amino acids generated from interstellar medium and processed and preserved in primordial solar system material. So the first step that we want to use amino acids as biosignatures is to determine are they really actively produced or they are the result of primordial synthesis. So that's the whole idea of the talk today. So I guess that all the people in this room know about Europa and Enceladus, so just want to mention very briefly. Europa is moon of Jupiter, is the size of a moon, and somewhat the internal structure is much like Earth. We have the metallic core with a rocky mantle. And the more exciting things for astrobiology is come from the presence of a salty subsurface ocean underneath the icy crust. And the evidence of the ocean came from two kinds of observations. One is the imaging data from Galileo spacecraft. We saw a lot of kinds of quiet things in here, which were hypothesized as we have the hot water coming from the oceans, came into the icy crust, so you have some kind, so there should be some kinds of activities in the past history. They are all now frozen, but there should be liquid water under the subsurface. Plus, with the fact that we saw a very less abundant impact crater, which is a very unusual for a planetary body object with a very tenuous atmosphere. So this suggests that the subsurface liquid ocean was something happened very recently. The more convincing evidence, in fact, came from magnetometer observations on Galileo. So Galileo had a magnetometer tracking the Jupiter magnetosphere, and in Europa is what in fact is detecting kinds of induced magnetic fields not coming from dynamo internal structure of Europa, but in fact that's where the induced magnetic field deflected from Jupiter magnetosphere. And so it suggests that there should be some kinds of conductive layer underneath the internal structure of Europa. And conductive more than water ice, more than liquid water, so there's only salty liquid water. For Enceladus, thanks to Cassini spacecraft, we have a lot of things we know, the science from the Plume. It's a global liquid ocean. The evidence coming from a lot of things from gravity data to confirm the existence of global liquid ocean, indeed coming from libration amplitude. If we're imagining, for example, like our Earth moon orbiting around our planet in a synchronous orbit, so theoretically we only see 50% of the moon. We cannot see the far side of the moon. But indeed, the maximum surface coverage that we could see the moon from the Earth is about 59%. Is because the libration phenomenon, in which we have the orbital eccentric, the orbit of the moon is eccentric. Plus, we have the tidal torque interaction between the Earth to the moon, so it's causing some oscillations in the viewing angles that the satellite looking at the planet. And the libration amplitude measure for Enceladus is so large that it cannot be explained by a two-layer internal structure model with just icy crust and a rocky core. So it should be some sandwich layer in between the crust and the core, and to be having some material be stable there, it needs to be liquid water. And we also found a lot of organics from the mass spectrometer and Cassini. Also with chemical energy, we detected molecular hydrogens coming from hydrothermal activities. So, as I pointed out from the first slide, so what the context the amino acids decomposition in the search for biological evidence in the ocean world. Hello? All right, sorry. All right, so we know that the amino acids was from previous talk, it can be synthesized and starting from intercellular medium and possibly a lot of other processes to synthesize amino acid in planetesimal, and it's preserved in primordial amino acid is preserved in a lot of primitive material like meteorite, comet, and asteroid. So to using amino acids biosignature, first step is we need to know is that really actively produced or they are something generated from primordial processes and preserved there in solar system building block material. And from chemistry point of view, the spontaneous decomposition of amino acids are known as among the slowest reactions that ever exist. For example, like glycine, the half-life about 1 billion years. For alanine is 10 billion years at room temperature, neutral pH. So by looking at the relative stability of the decomposition timescale of amino acids, so we can characterizing actively formed amino acids can be identified. So it's easier to, however, it's easier to said than done. It's just because we always have been, is not dealing with thermodynamics, dealing with kinetic, and everyone working on kinetic know the problem is we do not have very difficult to getting kinetic data to tracking with time. And many biologists here familiar probably much more understand better than me about the decomposition of amino acids by bacteria or other enzyme catalysts. However, it's not really applicable in this case. And from other point of view, getting the kinetic data is difficult because the reaction is super slow. So to getting something doing experiment in and to getting the data in lab time scale, we need to heat it up the solution so we can get the data in lab time scale, and also how to tracking all of that without interacting the system, also another thing that make it difficult. And so there are just only a few experiments done for applying to Earth hydrothermal system. However, for Earth hydrothermal system, water is heated up and it's go beyond critical state, so many physical chemical changes, positive changes for that. All right, so just want to point out what was happening there very quickly. So we have a lot of, so the behavior of amino acids is very complicated. So at least we have the deamination decarboxylation that leaving CO2. We have deamination that leaving ammonium. There may be other behavior like dehydrations or polymerization in here. So here's our analysis. So we collected all kind. We're trying to do the best, and of course we're trying to do some approach that with a simplified, but I think that's reasonable enough to. So we collected all kinds of kinetic data that we can have from published literatures. And we choose, there are a few criteria, but the most one is we choose only the kinetic data. That taken far below critical point water is because the water on the inside of the Europa is very hungry to be heated up to go beyond critical state. Also because the amino acid concentration is presumably far below water concentration around, so it could be treated simplified. We treated that the destruction rate is a first order reaction. So we considering two scenario with free dissolved amino acids in the ocean, and sometimes and the second thing that I pointed is mixture of amino acids. Basically is a kind of thing probably because near the seafloor, so the amino acid be in more concentration than the free dissolving around. So by this way, I can fit the data with the. Here is one of my fitted data. I just want to show you for serine and glycines with the R squared of at least 0.95% for the low of the red constant with inverse temperature. And of course, we want to do that because we know that the water, in fact, for Enceladus, the water, when it's cycling through the core, it must be heated up like to 323 Kelvin, 50 degrees Celsius. However, the mixing is not, the temperature of the water ocean is not really well constrained. It has some mixing that we do not really know. So by that way, you can finally solve the kinetic equation to find the decomposition timescale in function of temperatures. All right, so here's what we got with the, in here totally we got the result for 15 amino acids. The vertical one here is the decomposition timescale in year. It's not second here, it's in year. And the one here we're constraining that with the fluid temperatures. And at the first look, you will see that the destruction timescale depends very sensitive to ocean temperatures. And there are literature tools talking about that, where we have some, where we're increasing the temperature, so there'll be some kinds of weakening between the bond in the amino acids. Coming back, so what we got here is, it's hard to see. Okay, so here we have, I put in here some constraints. This dotted line, in fact, is about 10 million years. That is the time scale that the ocean on Enceladus will be stable. The upper constraint here is like 10 billion years. Of course, that is solar system time scale. Here is about the minimum temperature that will exist in the core of Enceladus. We unfortunately do not really know the temperature of Europa right now. But anyway, the point here is that if we look at the tree curve in here, for example, this red curve is for glycines, blue curve is for alanine, valine is a black curve. We'll look in here, there's even at 323 Kelvin, that the water is in liquid. So the time scale, the decomposition is about a billion years, which is very long. On the other hand, we have other things that, for example, other species like leucine or isoleucine is here, and we have methionine, which is the purple light here, that decompose relatively quick, even at a very low temperature. Let's say putting here like 223 Kelvin. And of course, quick in here means quick in geology time scale. And we have other kinds of amino acids as well. We have lysine, we have arginine. We have lysine here, we have arginine here, and histidine. Glutamic acid decompose also very slow. And it could probably, because when we heated up glutamic acids, it could transform into more stable form like pyroglutamate. So that would decompose in, let's say, billion year at 300 Kelvin here. And finally, we take that with some of the aromatic amino acids, and we have it decompose quite fast, even at the low temperature. It's just about 1 million year. So the second scenario that we consider in this study, so all of the scenarios that we calculated before is about the free dissolved amino acid in the ocean. But now, and so by free dissolved, there will be no other interactions with, it's just amino acid molecule with water surrounding, there will be no other interactions. But we have some other model with the mixing amino acids in the oceans, in which it's basically somehow analog to what we got in the seafloor. We have more concentrated in the ocean. So what we got here is the very quickly, even is even more quicker than the previous one for all kinds of amino acids. All right, so we go into the conclusion. So the conclusion here is that relatively short lifetime, and by short here is about less than 1 billion years of most amino acids except the 4 kind species, glycine, alanine, valine, glutamic acids, suggest that amino acids could be found there, could be detected on the ocean world. So their origins should come from an ongoing production rather than primordial synthesis. Of course, I am aware that there will be some of the limitation. However, the point here is to deriving the time scale rather than constraining exactly what the really the time. So there may be some variation with different pH that we do not really have data to constrain. But we're confident that the conclusion that in here. So of course, the next step is trying to distinguish between the distribution amino acids generated from geochemical synthesis versus young by biology, and that's it. Thank you.
Any questions for Ngoc?
So I'm a little ignorant about this, but so when you say Enceladus and Europa have a icy crust and salty ocean, do you mean that's water ice? And also, what kind of salts do we know? Any kinds of salts there? And the follow-up question after that is, did you consider those salts when you're thinking about the decomposition of the amino acids?
Wow, so yeah, so there is when I'm talking about the ocean here, I mean that there will be a liquid water underneath the icy crust. And it's powering by tidal heatings, as you know. I do not consider the effect of salt in this calculation. So now the point is that I don't think it will be affect the whole conclusion, because the one that we want to constrain here is the time scale rather than exactly the decomposition time. So it's true that there will be some variation if we take with pH, different pH and so on. I want to do that as well. The problem is that we do not have the data. So that's why we suggest that in October there will be the next meeting in Europa called Europa Deep Dive Composition. If anyone here would go, trying to see what is existing in the and what is the knowledge gap between experimental in modeling. So I would recommend if anyone interested in here to do some more experiment on that.
That was a very good talk, thank you. Kind of a follow-up question on that. One of the things we'd be curious about for Europa is how amino acids or other biosignatures are processed through the ice shell. And so not just surviving at ocean salinities of maybe 3% or 4% or whatever we might guess for Europa, but like brine concentrations upwards of maybe 40 PSU or that kind of thing. Have you or do you know of anyone who's worked on that, or is that also planned for the future?
So you want the distribution of amino acids in different case, or?
Yeah, so if amino acids get incorporated into the ice shell from the ocean and are preserved either in ice or in brine pockets.
Yeah, so that is my plan to working on that after that. The problem with Europa is that, you know, Enceladus, we have a very good compositions by Cassini. Europa, all the thing we know from the chemical composition, all the thing we know about Europa ocean is, wow, there is water there is salt there, and that is everything. Every of the composition discovered by Europa is just, assumption, for example, taking the rocky core with the composition similar to CM chondri or CV, whatever. So the thing here is that I'm trying to provide, a brief but a fundamental understanding of, wow, what if we go there, we found amino acids, so we can excluding at least the possibility of primordial synthesis. I would be very interested in to see what will be the distribution of amino acids from geochemical synthesis and biology, of course. The difficulty of that, we don't really know the composition of Europa ocean. The second thing is that the synthesis experiment for, let's say, geochemical synthesis, there are many people done that with, Fischer-Tropsch synthesis or Strecker synthesis. The problem is that we don't know to really calculate the distribution of that. We need kinetic data, and for all of now data, at least I saw there are only thermodynamic data. So for thermodynamic, we can calculate the free energy, whatever, in many conditions. It shows that it could be the free energy is negative, so we have, so we can say that, it could be happening, but we don't know really what would be the concentration.
Okay, let's thank Ngoc again.
Okay.